So now what I'd like to do is I would like to discuss a little calculus. My pre-calculus students have their final exam next week. I told them they'd be expected to know a little calculus. So we're going to present a couple problems and we'll attempt to use mastery level understanding, which means we're going to get the same answer in more than one way. If you'd like to call in, the number is 312-738-1060. I'll do the best that I can to answer whatever questions you have. I want to answer your questions. So call in. Okay, so here we go. Let's take a look. Little calculus. All right, so find the area in the first quadrant of a radical function in x is equal to 3. Find the area under the curve. Let's first graph it. Let's graph a picture of what we're looking at here. All right, so let's say we have the curve here. Boy, I wonder why that one young lady didn't call back. Boy. I was looking forward to finishing the problem out with her. Maybe she, well, I don't know what happened. Never mind. All right, so here we go. All we're doing is just about to graph. We're about to graph this problem to give you a picture of what we're working with here. All right, so a graph of the radical function looks like this. You put in 1, you get 1 back. You put in 4, you get 2 back. You're looking at a curve that looks something like this. All right, so you're working with the first quadrant. So you're working with a region that's in that first quadrant, and it's bounded by the x-axis. It's bounded by x is equal to 3, and it's bounded by this radical function. So one way of finding the area is to, let's set up this vertical slice. Set up that vertical slice like so. The area of this slice, I told my students the area of this slice, you need a height times a base. The height is the top minus the bottom. The top is radical x. So you take radical x minus 0, top minus the bottom, radical x minus 0. And what you're going to do is you're going to realize that the base of this slice is very, very small lateral distance. Let's call it dx. Let's call that base of this slice very, very small lateral distance dx. Now you're going to sum up these slices from one point of intersection to another. You're going to sum up these slices from the x value 0 to the x value 3. Now you're going to have to take the antiderivative of x to the half. Take the antiderivative of x to the half. Summed from 0 to 3. You end up with x to the 3 halves. X to the 3 halves. X to the 3 halves. And then you take 1 divided by that new exponent. You get 2/3. The old coefficient divided by the new exponent, you get 2/3. And you evaluate that from 0 to 3 using the first fundamental theorem of calculus. All right, so now, first fundamental theorem tells you to evaluate the upper limit using the antiderivative and the lower limit using the antiderivative. My students are going to have to do this on their own. So we get 2/3. This is the same thing as the square root of x to the third. All right, that's the same thing. 2/3 square root of x to the third. We're evaluating that from 0 to 3. All I did was rewrote this fractional exponent. So what we end up with is 2/3 times the square root of 3 to the third. I substituted the 3 right there. And then minus, substituting in 0 here. So you're just going to get 0. So let's simplify. It's just this minus 0. So let's simplify this. The way you could simplify this would be 2/3 times the square root of 3 squared. That's really 3 to the third. But what you could do is say the square root of 3 to the third. Another way to say 3 to the third is 3 to the second times 3. All right, so it's not very common. It's not a very common approach, but I'm hoping you follow what I'm saying here. All right, so let's continue this problem going upwards a little bit, So you end up with 2/3 times radical 3 squared, times radical 3. All right, you can break up a radical that way. So 3 squared, radical 3 squared is just 3. So this simplified would be 2/3 times 3 times radical 3. The 3's would cancel and you'd end up with 2 radical 3, final answer. So the area of this region is 2 radical 3 units squared. It's an area just like any other area. We're a long way from base times height though. We're a long way from base times height. If that wasn't clear, I want you to call in. If that wasn't clear, I want you to call in. All right, so let's use what I call mastery level understanding. I ask my students to know how to do problems in more than one way, and I want you to be the same way. I want you to be the same way. You can solve the same problem in more than one way. You're going to be like that one young lady who hung up the phone who I want to call back. She dominated the unit circle, and I want you to dominate your math subjects as well. Let's keep going. All right, so let's do the same problem in more than one way. All right, so let's draw the diagram one more time. Draw the diagram one more time. All right. Sorry, this is taking a little time. Maybe next time I'll have this already done, and that way we won't have to waste time with this little drawing here. All right, so we got 1, 2, 3, 4. 1, 2, 3. All right, so we got a point at 0, 0. You put in 1 into the radical function, you get 1 back. You put in 4 into the radical function, you get 2 back. The graph looks something like that. X is 3. So again, we're looking at this region right here. This region right there. So now what we're going to do is instead of a vertical slice, we're going to set up a lateral slice or a horizontal slice. And this very, very small vertical distance we're going to call dy. All right, so now one of the things that you'll discover is that when we have that lateral slice with a very, very small height dy, all this equation, which was y is equal to radical x, I want you to solve for x in terms of y. So we're still going to use this equation, but I want you to have the equation x is equal to something in terms of y. For you to make that happen, you're going to square both sides and get x is equal to y squared. X is equal to y squared. All right. So now let's find the area of this slice. This slice has a base of the right side minus the left side, right minus left. So right minus left, that would be 3 minus this curve, and this curve is y squared. All right, so right minus left, 3 minus the curve, 3 minus y squared. Common mistake is to say 3 minus radical x. But don't forget, I told you that when you got this lateral, when you got the dy there, everything's got to be in terms of y. All right, so that's the base. The height is dy. All right, so now what you're going to do is you're going to sum up this slice from the bottom to the top. So what we need now is we need this point of intersection. We need that point of intersection. Let's find it by setting the curves equal to each other. This point of intersection can be found by determining where this radical curve is equal to the linear curve. So the way you're going to do that is you say we got y is equal to, you can't see that. You got y is equal to radical x, and you got x is equal to 3. You can use the method of substitution. If x is equal to 3, you're just going to get y. You make the substitution 3 there, you get radical 3. So this y value here is 3 radical 3. All right, so that tells you that you're summing up these slices from the y value 0 to the y value up here, which is radical 3. All right, so again, our integrand is in terms of y, and our limits of integration are in terms of y. Common mistake here, is to keep the same limits of integration from 0 to 3. But we're summing this slice from a y value 0 to a y value radical 3. If that's not clear, I need you to call in. All right, so now we're going to take the antiderivative here. Take the antiderivative from 0 to radical 3. Or actually, I'm sorry, let's take the antiderivative now. All right, so we get 3y. You get 3y minus, you get y to the third. All right, and you take this old coefficient divided by the new exponent. You get 1/3, y to the third, and we're going to evaluate this from 0 to radical 3, the same limits of integration we found earlier. All right, so now let's make this substitution using the first fundamental theorem of calculus. All right, so we make the substitution, the upper limit, we get 3 radical 3 minus 1/3 radical 3 cubed. 1/3 radical 3 cubed. And then minus 0 evaluated at this this integration. We've integrated here. I want you to evaluate 0 here and here. It turns out you get 0, so I'm not going to write anything here, just minus 0. So the only thing we're going to do is just evaluate what we have here. So now what we have is let's simplify this down. We get 3 radical 3 minus 1/3. Another way to evaluate radical 3 cubed is radical 3 squared times another radical 3. That's the same thing as radical 3 cubed. All right, so if you keep going, you get 3 radical 3 minus 1/3 radical 3 squared, that's just 3, times the radical 3, which is here, so you end up with 3 radical 3, 1/3 times 3, that cancels, and you end up with minus radical 3. 3 radical 3, oh, we only got 1 minute left. 3 radical 3 minus 1 radical 3 is 2 radical 3. Notice how we got 2 radical 3 here, and we got 2 radical 3 here. That's called mastery level understanding, and that's what we're expecting from our students.